If a rotary phase converter starts with two phases that are 180 degrees apart, it can't possibly make proper three-phase power that's 120 degrees apart, right? Right? Welcome back to Cloud 42. I'm James. In my last video, I wired up a rotary phase converter. If you haven't seen that or don't know what a rotary phase converter is, that video would be a good place to start. But the TLDR is that a rotary phase converter takes the single phase power available in most home shops in North America and other parts of the world and generates three-phase power to run machine tools. So far, so good. But the comment sections on phase converter videos and the hobby machining forums are full of confused people questioning how this can be possible. The argument goes like this: since the 240 volt power provided from the wall is really just two 120 volt phases 180 degrees apart, and the phase converter is just generating a third phase to go with those two, the resulting three phases can't possibly be evenly spaced. They can't possibly be 120 degrees apart because math. In fact, they can and they are. How is this possible? Let's dig into the theory a little bit, and then I'll get out the oscilloscope and we'll measure it for real. Keep in mind that while I am an engineer, I'm not a tradesman, so I'm going to use all of the wrong words to describe things, and that will give you something to talk about down in the comments. As we talk about three-phase power, we are going to talk about voltages. And it's important to understand that when you talk about the voltage, it's very common to talk about the voltage on a wire, but just taking one probe and measuring the voltage on a wire or on a terminal doesn't really make any sense. You have to measure the voltage between 2 points in a circuit, like between a hot wire and a ground. The screw on this outlet is grounded. And you can see from this leg of the circuit to ground's 120 volts. From this other leg of this circuit to ground is also 120 volts. But if I measure between those two terminals, the voltage is 240 volts. So what's the voltage on that wire? Is it 120 or is it 240? And the answer is, it depends what you're measuring it in reference to. So keep this in mind. This is why meters have two probes, and that is one of the key elements that gets people confused when talking about three-phase power. In order to talk about three-phase power, we have to talk about the concept of phase and what that actually means. And to talk about phase, we have to talk about sine waves. A sine wave or a sinusoid is generated by the rotation of a circle geometrically. So if we take a circle and rotate it and we pick a point on that circle and we track the y coordinate in the vertical motion as that circle rotates, over time, that will trace out the shape of a sine wave. And this isn't terribly surprising that AC power is in the form of a sine wave because it's actually generated in a generator with a rotating magnetic field across a coil of wire. So as that generator rotates, it generates voltage proportional to the position of that coil. So what is phase? Well, the phase refers to the angle of rotation of the circle at a certain point in the sine wave. So there's a diagram here at the top of the Wikipedia page that shows this. So if we talk about the sine wave starting at 0 degrees, if we rotate the circle 90 degrees, it reaches its peak. We rotate to 180 degrees, it reaches 0 again. At 270 degrees, it reaches its negative peak, and at 360 degrees, one full revolution, it reaches 0 again. So we talk about one full waveform or one full period of the sine wave as being 360 degrees. So if we want to talk about things that happen in terms of timing during that sine wave, we can describe the position in that waveform as a number of degrees of rotation of the circle. So in the case of two-phase or three-phase power, we have a couple of waveforms that are offset in time, and we can describe how much they're offset in degrees of rotation of the circle. So there's another diagram down here on the Wikipedia page for phase that shows this. If we have two waveforms here shown that are out of phase, meaning they are shifted against each other in time, you can describe how far apart they are as an angle in degrees. So if we're talking about the power that you see coming from the wall, usually in North America, you generally have two phases. And if you measure them with respect to the neutral, talk more about that later, they will appear to be 180 degrees out of phase, meaning that when one waveform reaches its maximum, the other waveform is reaching its minimum. They're out of phase by exactly 1/2 of the rotation of the circle, or 180 degrees. When we talk about three-phase power, we talk about three sine waves that are out of phase by 120 degrees, so they span equally around the entire circle. So we have one waveform that starts here and ends here. The next waveform starts 120 degrees later. The next waveform starts 120 degrees after that, so they are spaced evenly around the circle. So the job of the rotary phase converter is to convert our two input phases that are 180 degrees apart, or a single input phase, we'll talk more about that in a minute, into a three-phase output that's spaced at 120 degree intervals. Now, how does it do this? It doesn't seem intuitive. How do you take something that's 180 degrees out of phase and change it to something that's 120 degrees out of phase? You can't do that, especially since it's passing through the input to the output. But that's only true if you're thinking in terms of reference to the neutral. If you can free yourself from that concept, it's easier to see what's happening here. I've said several times that these waveforms appear the way they do when measured with respect to neutral. Well, let's talk about what neutral is and what that means. The most common wiring distribution configuration that's in homes and businesses, farms, whatever, in North America is 120 volt or 240 volt split phase. Now, what that means is you have a transformer that is supplying power to the building, and you have a single 240 volt AC phase that's being provided as input. That is run through a transformer that is center tapped. So you have a center tap on the transformer that is then bonded to the earth ground, and that's called the neutral. So what's actually coming into your panel is a neutral that's referenced to earth ground, and then two legs of power that are each 120 volts AC with reference to that neutral. Now, I say with reference to the neutral because if you measure them with reference to each other, it's 240 volts AC. So if you ignore the neutral, you have 240 volts AC. This is commonly used for heaters, stoves, clothes dryers, air conditioners, and other high power appliances. They're run directly off of this 240 volt AC. Lighting and outlets in the wall are typically run off of one of these 120 volt legs. If this is the standard configuration for single phase power or split phase power, well, what about three phase? And the answer is it depends. There are a bunch of different ways that three phase power is provided and wired into buildings. The most common that you'll find here in North America is called the Y configuration, often just spelled WYE, but it's in the shape of a Y. And you have three phases of power, A, B, and C, and a neutral. So you've got four lines plus a ground. The neutral is ground referenced, just like it is in the 240 volt split phase. And then each of these legs is 120 volts with respect to that neutral, but out of phase by 120 degrees. So the waveform looks like this. Now you can see this is peaking above 120 volts. It's actually up around 169 volts. And that's because that 120 volts is RMS. That's a root mean square measure of the voltage. The actual peak of the voltage is higher than that. So if you're looking at A or B or C with reference to the neutral, you're going to see 120 volts RMS on each one of those. If instead you measure between them, between A and B, between B and C, or between C and A, just like when we connect a 240 volt load across both phases of the residential wiring, if you connect across any two of these phases, you're going to see 208 volts AC. And of course, the peak of that is higher than 208. So if you've ever wondered where that 208 volts comes from for three-phase power, it's because of this configuration. Well, why is it done that way? Why isn't it 240? Well, it's done as 208 because that makes each one of these phases 120 volts. And that is very convenient when you have a building where you're going to have three-phase high power loads, but you also are going to have lights and outlets, and you need 120 volt circuits as well. This allows you to wire up your 120 volt breakers across a single phase to neutral, and you have that 120 volts in the panel. But if you put in a triple breaker and tap all three phases, you have your 208 volt three phase. So that brings us to the other kind of configuration that we commonly see, and that's called three-phase delta. The difference between three-phase Y and three-phase delta is that the delta has no neutral. You simply have your three phases. They're labeled XYZ here. They're sometimes called XYZ. They're sometimes called ABC. They're sometimes called L1, L2, L3. But you only have those three legs, and if you measure the voltage between any two legs, you will see 240 volts. So that's actually higher than the 208 volts. And the reason for that is because we don't have to worry about making these individual legs 120 volts to the neutral, because there is no neutral. So you don't have to run a wire for the neutral. So you save money on copper, aluminum, bus bars, and all of the hardware associated with routing that. You don't have to pay for any of that. The downside, of course, is you don't have the neutral, so you don't have the ability to directly connect 120 volt loads. But if all you're running are three-phase loads, delta will work fine, and it's a less expensive option. What do you do if you have a three-phase delta configured power system and you still need to run 120 volt loads on it? Well, there is a third common configuration, and this is called high leg delta. It's also referred to as wild leg delta or bastard leg delta less commonly, and it is configured like this. You have two of your phases that are two of your legs that are 240 volts AC between them, and you use a transformer that produces a center tapped neutral that's then referenced to ground. So you have this 240 volt phase, exactly the same as the one that you have in residential wiring with the center tapped neutral, where here you can connect 120 volt loads between the neutral and either one of these legs. And you can do exactly the same thing here. You can connect your 120 volt loads between the neutral and either C or B. Now, with the rotary phase converters, these are actually A and B, not C and B. At least that's the way they're labeled on mine. It may vary on yours. The point being that you still have three phases, A, B, and C, that are 240 volts, 120 degrees out of phase with one another, but one of those 240 volt phases is center tapped. Now, in the case of the rotary phase converter, this is the input. You already have this configuration coming from the wall with the center tap transformer, and you're simply feeding that into the rotary phase converter, and it is producing the third leg. I believe on the American Rotary ones, this is labeled C, so just kind of don't worry about the letters, but this is what's happening. It's generating this third leg, also called a high leg or a wild leg, to complete the three legs of the three-phase output. What happens if you grab a meter and start measuring this? Well, you will see something that looks like this. Since you're measuring everything with respect to neutral, if you look at C and B, or A and B, on the phase converter that I have, you will get a plot that looks just like this. It's just like what you would have seen as the output of your center tapped home wiring. You see this, plus then you see the third leg, the wild leg, at a much higher voltage, offset 90 degrees from those two. So when you read in the forums or you see somebody down in the YouTube comments who says that a rotary phase converter does not produce real three-phase power with 120 degree phase separation, that's because they're measuring with respect to the neutral, and they're looking at something that looks like this. And sure enough, I see two phases that are 180 degrees apart, and I see the third phase generated at a higher voltage, 90 degrees between them. So the people that write that are not wrong. They're just not taking a relevant measurement. And we've definitely seen this. In the last video, I got some comments from a viewer who had hooked up a power quality analyzer and saw a waveform that looks very much like this. If you look at this and you look at this, you're seeing exactly the same thing. You've got the two phases, and you've got the third that's generated at 90 degrees between them. But there's a clue right down here at the bottom of what's going on. He's got this configured for three-phase Y, but we're not looking at a three-phase Y system. We're looking at a high leg delta configuration. So what's happening is it's measuring this waveform with respect to neutral. Well, what happens if you instead ignore the neutral and just measure from A to B, from B to C, and from C to A? Well, if I take exactly this plot and exactly this data and say, okay, well, let's measure between the yellow line and the blue line and plot that. Let's measure between blue and purple, and then let's measure between purple and yellow and plot that. And this is what we get. We get nice, evenly spaced 120-degree phases, all at the same amplitude. Well, how is that possible? Well, let's just take a close look at the graph. Let's take a look at the yellow line right here at position 0. If we take the yellow and subtract the blue, well, right here, we're a little bit under 300. The blue is at 0, so we would expect at this point our yellow phase relative to the blue one to be at a little under 300, and that's exactly what we see. Well, what about out here where they cross? Yellow minus blue, if they're the same amplitude, well, then that point should be at 0. And so right at that point, the yellow line here is crossing 0, halfway between 1 and 2 on the graph. Halfway between 1 and 2 on the graph is where they cross. So as non-intuitive as it seems, if you actually are taking the difference between these crazy waveforms being generated by the rotary phase converter, you get nice, neat three-phase power. The thing you have to understand, though, is that this is not centered around the neutral. The neutral is instead referenced to the center tap of one of the phases, as opposed to, as in a Y configuration, being the center of the three phases. So this is where all the confusion comes from. People are expecting a Y configuration, and the output of this thing is not a Y configuration. It's a high leg delta. While I like theory as much as the next person, probably more if we're being honest, let's see if this works in practice. I've got my rotary phase converter here, and I have a plug disassembled and twist locked into the receptacle. And I've got some pieces of aluminum TIG rod screwed in under the terminals. I don't recommend this. Don't touch the TIG rod. You will have a bad day. And then I have my Rigel 4-channel oscilloscope here, and I've got it configured with some differential probes. Now, you could use a standard 10x oscilloscope probe as long as you're measuring everything with respect to ground. The differential probe, however, allows you to measure between two high voltage terminals, both of which have a potential relative to ground. So this is really what you need to do if you want to take these measurements safely and not blow up your scope. Let's start by just taking one of these probes and measuring across the 240 volt input. Now I have this plugged in, and even though the phase converter is off, the input 240 volts is passed through. And you can see, we put the probe on it, we're seeing a nice 240 volt RMS waveform. This is exactly what one would expect. Now, if instead of measuring across that, we measure from one side to ground, we also see a sine wave with a little bit lower amplitude. And if I light up a second channel and measure the other side, we see the two 120 volt waveforms 180 degrees apart, exactly as expected. We go ahead and put a probe on the wild leg and start the phase converter, we see exactly what we expect. We've got the two 120 volt phases with respect to neutral and the 208 volt wild leg 90 degrees between them. This is, of course, exactly what we saw on the power quality analyzer photos. Thank you, Jason, for sending those in. Of course, that's not what you're here to see. Let's move the probes around. We'll probe from A to B, from B to C, and from C back to A, and start the converter. And as you can see, we have three phases 120 degrees apart. You can see some amplitude differences. The yellow is the input phase, and you can see that the other two phases relative to the wild leg are a little bit hotter, and that's just because there's no load on the converter. And once we add a motor and actually start loading this thing down, these should even out and the balance should be better. I can get the font size turned up so you can see it. We can see here that the phase angle between 1 and 2 is measured at 120.4 degrees. Now, if we just let this free run, it does jump around a little bit because this particular scope is having a little bit of trouble locating the zero crossings, but what it's measuring is close enough to convince me that it's correct. There has been enough confusion about this topic that American Rotary actually addresses it in their FAQ. They've got a couple of questions out here. One is, why is the output voltage on my 240 volt phase converter 208 volts to ground? And the answer that they give is that they're passing the two incoming power lines directly through and generating a third leg. And they're calling out that this is a high leg delta configuration. This will power most three-phase machines. Some machines, however, require Y configured power, which includes a neutral. If your machine requires this, then you will need to run it through a delta to Y isolation transformer. There's another question further down asking, can I use it to run equipment that requires a neutral? And the answer is yes, but it's delta configured, meaning it has no neutral. You will need a delta to Y isolation transformer. Well, if you pop out to Wikipedia, they actually have some information about delta Y transformers and how they work. And essentially you have two sets of coils, one configured as delta, one configured as Y. So you can take the output of your rotary phase converter, feed it into the delta windings. This is magnetically coupled across, and it energizes these other coils that are in the Y configuration with a center point reference. You take that center point reference and you attach that to ground, and presto, you have a neutral ground referenced Y configuration power source. And you can buy these, but for most home shops just running three-phase equipment with three-phase motors, you don't have to worry about this. You can just use the three-phase delta and ignore the neutral completely. I hope this was helpful. This is a complex topic, and while there's a lot of good information out on the internet, most of it's aimed at engineers and expressed in terms of equations and phasor diagrams. Even the stuff that's intended for electricians is often mostly industry jargon and procedures for connecting equipment. If you enjoyed this or found it useful, give it a thumbs up, join in the conversation down in the comments, and maybe consider supporting the channel on Patreon. Patrons can download drawings and files for all of my projects and get a peek behind the scenes. Thank you for watching.